Hello everyone, I want to welcome you to another section, and in this video I'll be going further on how to calculate the maximum absorption wavelength for another class of compound. In the previous video I have talked about how to calculate the maximum absorption wavelength for conjugated diene. But in this video, I'll be talking about how to calculate the maximum absorption wavelength for conjugated carbonyl compounds. Some of the principles used in calculating the maximum absorption wavelength for conjugated dienes are also applicable in calculating the maximum absorption wavelength for conjugated carbonyl compounds. So I'm going to be highlighting some of those steps and principles to follow in calculating the maximum absorption wavelength as highlighted in the previous video, but I'm only going to be adding some little additions to some of those things I said in the previous video. So in calculating the maximum absorption wavelength of carbonyl compound, these are some of the steps that you have to follow. The first thing is to identify the chromophore that is present in the given compound, that is the part of the compound that is absorbing the radiation, in this case the UV. Now, and the chromophore can be some of these highlighted chemical groups, and I'm going to talk about them much better later. Another thing to do is that after you have identified the chromophore in the given compound, you also have to number, or you have to identify each of the carbon after the carbonyl carbon. So the carbonyl carbon is the carbon carrying the double bond O, which carries the what? The functional group. Now you have to identify or number the what? Every carbon after the carbonyl carbon by what? With all of these Greek letter, using your alpha, beta, gamma, delta until the last carbon in the conjugation system. So after you have identified the carbons and you have numbered the carbon with the Greek letter, the next thing is now to identify the additions or the oxochromes that are directly attached to the conjugation system. But the only difference that occurs in the case of conjugated carbonyl compound that is not in what? In conjugated diene is the fact that different attachments, or let me say different additions that are directly attached to the chromophore, they have different values at different positions. For example, now for conjugated dienes, if you have an alkyl residue, or if you have a ring residue or an alkyl substituent, the value for that particular oxochrome, or let me call it addition, is +5. You add +5 to the parent value. But in this case now, the position of the alkyl substituent or the ring residue matters, because the lambda value for the alkyl substituent or the ring residue varies with position. So in this case, if alkyl residue is at the alpha position, the value you are going to add to the parent value of the compound is +10. If the alkyl residue is at beta position, you are going to add +12. If it is at any other position apart from this alpha or the beta, you add 18 to the parent value of the given compound. If you are having chlorine as an addition or an oxochrome that is attached to the conjugation system, and if the chlorine is at the alpha position, you add 15. But at any other position apart from this alpha, you add 12 to the what? To the parent value of the given compound. But for acetyl, if you have an acetyl substituent, the value you are going to add at any position for that acetyl will be with what? You add +6 to the parent value. At the same time, if you are also having a double bond extending conjugation, whatever the position does not really matter in that case, you add 30 to the parent value of the given compound. So, but the major thing to note is that when calculating the maximum absorption wavelength for conjugated carbonyl compounds, you have to consider the position of the substituent. that are directly attached to the conjugation system, because the value of the substituent varies with the position. So that's a very important thing to note compared to what we have under conjugated diene. Now, after you have identified the chromophore, you have number or identify the carbons after the carbonyl carbon with the Greek letters, and you have also identified the additions or the oxochromes, which will also give you some lambda values that will be added to these parent values. Then you can now sum up all the lambda values to get the maximum absorption wavelength for the given compound. In this video, I will be calculating the maximum absorption wavelength of one or two compound as an example for us to follow. To talk a bit about the chromophore, in a given conjugated carbonyl compound can be any of these mentioned chemical group. One, you can have an acyclic ketone. If you have an acyclic conjugated ketone, then the parent or the basic lambda value for that compound will be 215 nanometer. Now, if you are also having a 6-membered ring conjugated ketone, then in that case also the basic or the parent value for such compound that have that kind of chromophore will also be 215. Last, you can have something like this. So this is an acyclic ketone that is conjugated. This is a 6-membered ring ketone that is conjugated. So for any of these as being present in any given compound of conjugated carbonyl compound, the basic or parent lambda value for them is 215. Another one that you can also have as chromophore in a given conjugated carbonyl compound is that you can have a 5-membered ring ketone, conjugated ketone. So in this case, you are having this and you are having this. So this is a 5-membered ring ketone, and the basic value lambda value for this 5-membered ring ketone is 202 nanometer. Another kind of chemical groups that you can also have for a conjugated carbonyl is that you can also have a conjugated aldehyde. So this is an aldehyde, but it is conjugated. So for a conjugated aldehyde compound, the basic lambda value there will be 207 nanometer. In the same manner, we could also be looking at a conjugated ester or carboxylic acid. So, but for those two kinds of compounds, the basic or the parent lambda value for this chromophore is 197. So these are some of the chemical groups that can serve as a chromophore in any given conjugated carbonyl compounds. And the first thing to do is to identify which one of these is present in any given compound before labeling or identifying the carbons after the carbonyl carbon with the Greek letter, and then finding your substituents that are directly attached to the chromophore. Then you can now get the maximum absorption wavelength by summing up all the lambda values of the chromophore and also of the substituents. At this point, I will want you to know two particular things under calculation of maximum absorption wavelength for conjugated carbonyl compound. First, the sp3 carbon that is directly attached to the carbonyl carbon, the sp3 carbon that is directly attached to the carbonyl carbon is not counted as a ring residue. That's the first thing to note. The second thing to note is that in some cases, the conjugated system can be along the two sides of the ketone functional group. For example, I could have something like this. I have this, I have this, and I have this. In this case, the carbonyl double bond is conjugated along this side. At the same time, the carbonyl double bond is also conjugated along this side. So the conjugation system can be along this part. It can also be along this part. Now, but in calculating the maximum absorption wavelength of such conjugated carbonyl compound as this, you take the conjugation system that have the longest carbon chain. So in this case now, my conjugation system for a compound like this will be along this particular part, because it has the longest carbon chain. So these two things I've mentioned are things to take note when working with a conjugated carbonyl compound. In conjugated carbonyl compound also, you can also have isocyclic double bonds, and the value is still the same as you have it under the conjugated diene. For each isocyclic double bond that you have in the conjugated carbonyl compound, you add +5. So, and these are some of the things to know when trying to calculate the maximum absorption wavelength for conjugated carbonyl compound. At this point, I would like to do some examples so that you can have an understanding of what I have said so far. Now, let's consider this example, this compound, which is a ketone and it is also a conjugated ketone. Now, the reason why we call them alpha beta unsaturated carbonyl compound is because the double bond that we have there is between the alpha and the beta carbon. But note that the conjugation system can extend beyond this point. So the first thing I'm identifying there is that the chromophore in this compound is an acyclic. We have an acyclic ketone, and the parent standard value will be what? Will be 215 micrometer, because we are having an acyclic ketone in this particular given compound. Another thing, like I said, is that after you have identified the chromophore, you have to number, or you have to identify the carbon after the carbonyl compound along the conjugation system part. In this case now, this the first carbon after the carbonyl carbon. This is the carbonyl carbon. The first carbon after the carbonyl carbon is alpha. This is beta. So you can stop at that point. So because you stop at the last carbon involved in the conjugation. So this is alpha carbon. This is beta carbon. In a way, I can also trace out my conjugation system like this. So this is the conjugation system. So after I have numbered or identified the carbon after the carbonyl carbon with Greek letters, the next thing is for me to identify the oxochromes or the additions. One, in this case now, at the beta position, we have an attachment of an sp3 carbon, which we can call an alkyl substituent, or we can also call it a ring residue. So this is, as it were, a ring residue. This one also is an sp3 carbon. The carbon here is also an sp3 carbon, but the sp3 carbon here is attached to the carbonyl carbon, so we don't take it as a ring residue. So, and I've mentioned that earlier, that for every sp3 carbon directly attached to the carbonyl carbon, you don't count them as a ring residue. So in this case now, we only have one ring residue. And I've said most times we use ring residue and alkyl substituent. You can always use them interchangeably. So for this one ring residue that we have at this place, plus what? Plus 12. Now, if you look at this compound now, there is no other substituents or additions directly attached to the what? To the chromophore, apart from this sp3 carbon attached to the beta carbon. And therefore, our maximum absorption wavelength for this compound would be 227 nanometer. That's for this particular compound. Another example that we are going to consider is this. Now, in this compound now, we are also having a ketone, because this is a ketone functional group. And between this carbonyl double bond and the double bond that we have here, there is a single bond. that implies that they are what? They are conjugated. Between this double bond and this one too, we also have a single bond. That implies that we have the what? Conjugation. So I could say I have this conjugation system. So these are conjugation system in this case. So after identifying the conjugation system, we can now identify what is the chromophore in this particular case. The chromophore in this case will be that we have an alpha beta unsaturated 6-membered ring ketone, because this ketone functional group is part of a what? A 6-membered ring, which is 1, 2, 3, 4, 5, 6. So that's what makes it a what? An alpha beta unsaturated 6-membered ring ketone. So, and the basic value for this, let's say this is the lambda. The basic value for this particular chromophore is 215 nanometer. So we are going to have 215 nanometer. Now, in this case, after we have gotten the parent or the basic lambda value for this compound, the next thing to do is to identify the carbons after the carbonyl carbon along the conjugation path. So this carbon here will be our alpha carbon. The carbon here will be the beta carbon. The carbon here will be the gamma carbon, and the carbon here, the last carbon in the conjugation system, will be what? The delta carbon. So this is alpha, this is beta, this is gamma, and this is the delta. So that's the next thing to do after identifying the chromophore and the basic lambda value for that particular chromophore. Now, after this point, the next thing is now to look out for what? For the additions or the oxochromes that are directly attached to the to the conjugation system. First, in this case now, we are having 3 conjugated double bonds. So, and we have said in the previous video that anytime we have more than 2 conjugated double bonds, 2 of the 2 will help us in getting the basic lambda value, while the other ones will be double bonds extending the conjugation. So in this case now, we are having this basic 2, and this third double bond will be a double bond extending conjugation. So in this particular compound, we are having a double bond extending the conjugation. First, and for a double bond extending conjugation, we said you are going to add plus 30. So this will give us plus what? Plus 30 due to double bond extending conjugation. So this is plus 30 here. Now, another thing, what are the other things that we can also have in this case? So let's try to identify the ring residue that are attached to the what? To the conjugation system. First, we have an sp3 carbon here. So this in a way a ring residue. We have an sp3 carbon here. We have a ring residue, and we also have an sp3 carbon at this point. So we have a ring residue. But like we said earlier, that the position of attachment of this ring residue matters in getting the value for each of them. Now, the first is that this sp3 carbon at this point is attached to the alpha position. So, and for a ring residue or a piece of substituent at the alpha position, you had plus 10. So there we are also going to add plus 10 due to a ring residue attached to the alpha position. Here also at this beta position, this sp3 carbon is attached to this beta position. So that means you are also going to add plus 12 nanometer because of the ring residue of the sp3 carbon attached to the beta position. And at the gamma position, there is no alkyl substituent or ring residue attachment. So that we are not going to add anything. At the delta position, we are also having attachment of an sp3 carbon at this point. So an sp3 carbon is attached to this delta position, which we can also say we are having an alkyl residue attached to the delta position. For an alkyl substituent or ring residue at this delta position, we had plus 18. So here we are also going to add 18 nanometer. Now, another thing also to consider is that we don't have alkoxy substituents, we don't have chlorine as substituent, we don't have acetyl substituent. But in this compound, we are also having isocyclic double bond, because if you look at this double bond in the middle, it is outside this ring. This double bond here is outside this particular ring, and it is directly attached to the what? To this ring system. So that makes it what? Isocyclic to this ring. So when you have a double bond outside a ring and it is directly attached to that ring, we call it an isocyclic double bond. This same double bond also is outside this ring below, and at the same time it is attached to the ring below at this point. That also makes it what? Isocyclic to this ring. So we can say here that we are having what? Two isocyclic double bond, and that will be plus what? Plus 10, because for each isocyclic double bond we had plus 5. So because we are having two isocyclic double bond in this case, we will add 10 nanometer. So the sum of all of these lambda value will give us the maximum absorption wavelength for this particular compound. So if we are going to do the summation now, 215 plus 30 will give us 245. 245 plus 10 will give us 255. 255 plus 12 will give us 262. 262 plus 18 will give us 280, and 280 plus 10 would give us 290. And that means the lambda max value for this compound, summing all of these together, will give us 290 nanometer. So that's the maximum absorption wavelength for this particular compound. So these two examples are what I will be talking about in this particular video. If you have any questions or anything that is confusing about this particular aspect of calculating the maximum absorption wavelength for conjugated carbonyl compound, you can drop it in the comment section. I will do well to respond to your questions in the comment section. I want to encourage you to keep watching at the same time, not just to watch but also to subscribe to this channel. And I also want to plead with you to help us in sharing this video with your fellow students who you know can also be in the need of this lesson. I want to appreciate you again for watching the video and expect more on this particular channel. Thank you for watching, and don't forget to click the subscribe button. Thank you.